Hi, this video is going to be on areas bound by the y-axis this time. So there'll be some similarities with the last concept with x-axis, and we can use our knowledge from x-axis bound areas to solve some y ones. So we'll just get stuck into it by I'll do the first problem, and I'm going to do it in 3 different ways. So let's read it out. Find the area bounded by the y-axis and y equals root x, y equals 0 and y equals 3. So just like with x-axis, first thing we're going to do is of course draw up a diagram. So the graph of root x, if you remember, looks like this. And we're looking from y equals 0 up to y equals 3, and bound with the, we're not going to go past the y-axis, we're looking for this area here. So there's a few different ways we can do this. So if you notice, if we knew what this point was down here, right, then this would actually kind of square off and make, in the yellow here, this would be a rectangle, right? This big yellow area. Then, using what we learnt from the last concept, we could find this area here underneath the curve, right, bound by the x-axis, and then we could subtract that away from the rectangle and we'd be left with the yellow area. Okay, so here is one method. I'm going to call it subtracting rectangles. So we need to first find out what's this point here. Well, we know the y value is 3, right? So we just need to find the corresponding x value. So we know when y equals 3, this means 3 equals root x. So to reverse a square root, we'll square both sides, and this means that x equals 9. So what's the area of the square? Sorry, not the square, the rectangle. Right, well now the big rectangle is going to be an area of 3 by 9, which will be 27. And then we can subtract away the area under the curve, bound by the x-axis here, from 0 to 9. So that's, we're going to subtract away the area from 0 to 9 of square root x, which I'll write with the power. And then if we do the rectangle, so if we do the rectangle here, that's probably misleading because that just looks like the final yellow piece. I did originally do the rectangle yellow minus the the green piece. Hopefully you can visually see that. So 3 by 9, easy enough. 27 minus, now the integral, we've got x to the power of a half. We're going to add 1 to the power. Makes it 3 over 2, and divide by the new power, 3 on 2, and we're going from 0 to 9. Then we've got, this is x cubed, and over 2 in the power means square root, and 3 over 2, when we divide by a fraction, we can times by the reciprocal. Okay, I'll just go up here. So now we can calculate this by substituting in 2 times 9 cubed on 3 minus when we sub in 0. Okay, so this bit here, 0 cubed times some stuff and divide by some stuff is 0. Now here, remember you can do these in either order. Of course you can put this in your calculator, but I'm just doing it in my head. So you can do the square root first. So square root of 9 is 3. So we've got 3 cubed is 3, 9, 27. 27 over 3 is 9, and 9 times 2 is 18. So this is 27 minus 18, or if you just threw the whole thing in your calculator, you would get that this is 9 square units. Okay, so that was one method by finding a bigger rectangle and then subtracting an area bound by the x-axis, and the result was an area bound by the y-axis. So I'm going to do the exact same problem, so give me a second and I'll just redraw the diagram. And we're looking for this area here. So really with the hopefully I emphasize this with you know, looking at the symmetry with even and odd functions and that kind of thing, or symmetrical pieces like in the sine wave above and below the x-axis when we were doing bounded by the x-axis. So here as well, you really got to think geometrically, right? You notice we can do a rectangle minus the piece below and we're left with the other piece. Now something else you might notice here geometrically is, right, y equals root x is a rotated parabola. Sorry again. Is a rotated parabola on its side. So if we were to rotate this, just spin the whole thing 90 degrees to the left, right? Let's go spin the whole thing 90 degrees here, right? Well, what kind of graph would we have? Well, we'd have this bit of the parabola would be here, and 3 across to there would be across to -3, 0 would still be fixed there. And now it's the graph of y equals x squared. So we can find the area under that curve just using our knowledge with areas bounded by the x-axis. So method 2, we'll call this rotating to x-axis. So now we've noticed that there's two equivalent areas, but it's now in a format that we would have been able to do from last lesson. So the area, it's above, everything's above the x-axis, so it's going to be positive, so we don't need to worry about absolute values. So we're going to find the integral from -3 to 0 of x squared dx, add 1 to the power, divide by the new power. From -3 to 0, we'll sub in 0, minus sub in -3, 0 minus, that's -27 on 3, minus becomes plus, and minus becomes plus, and 27 over 3 is again 9 square units. Right, so that was, we were able to rotate it onto the x-axis. So if you can kind of see that visually. Now, like I said, I was going to do 3 different methods of the same problem. So again, I will draw up the diagram. So, just like we can integrate with respect to x with stuff bound on the x-axis, we can actually do the same thing with integrating with respect to y when we've got values on the y-axis. So to do this, though, notice, for example, up here, we had a function y was a function of x, right? So just notice here, right? Notice y is a function of x, was that piece up there. So what that meant is we could then integrate our function with respect to x over this range on the x-axis. So if we actually have a function of y, so we have if x is a function of y, which we currently don't have over here, right? We've got y equals a function of x, but we can format this with some equation skills and write it x as a function of y, and then we can integrate with respect to y. So how can we do that? Let's call this method 3. Oh. Method 3, x as a function of y. So if y equals root x, so we can get x as the subject, we'll square this because we'll cancel out, and now we'll have x equals y squared. So because we've got x as a function of x as a function of y, we can integrate y squared with respect to y over this range of y values from 0 up to 3. And again, you might notice some symmetry here, right? X squared with respect to x 0 to 3, y squared with respect to y 0 to 3 is going to turn out to be the same thing. So if we're integrating y squared with respect to y, same process, add 1 to the power, y cubed, divide by the new power, and we're going from 3 to 0. So if we sub 3 in, we get 3 cubed on 3 minus 0 cubed on 3, which is 3 cubed is 27, over 3 is 9, minus 0 is 9 units squared. So again, 3 different approaches, but we got the same result with all of them. So they're not all going to be the best or even usable in every scenario, but it's good to have all these different, add these different methods to your repertoire. So you've got a toolkit to be able to tackle any problem. And really the emphasis is that you've got to think really geometrically about any kind of symmetry and that kind of thing that you can see in these problems. So let's do question 2 now. We've got y equals root x, which is again the same equation. But this time it's not from 0, it's from 1 to 3. Whoop. That's a bit too unco. Okay, so any of these 3 approaches are technically usable here, right? You could see you could rotate this 90 degrees to the left and rotate it down onto the x-axis, and find some equivalent function and do an area bounded by the x-axis. You could do this with rectangles. Now with the rectangles it's a little bit confusing because you'd actually want to go from this point to this point, find this area under the curve. So you'd want to do this, I'll rub this out in a second, you'd want to do the big rectangle here So you'd want to do the big green rectangle minus the orange bit under the x-axis, and then minus this other little square in here, right? Because that'll block off and make a, sorry, not necessarily a square, here it is, but that'll make a rectangle. So you want to do the big rectangle minus a little rectangle, and then minus this area under the curve here, which would be doing y equals root x, so integrating x to the half from whatever this x value is to this x value, which again you'll need to find by subbing these numbers in. They'll be 1 and 9, okay? But let's practice. Once I rubbed all these out. Beautiful, didn't rub out any of the actual diagram. So let's try doing this as a function of variable y, so method 3. So again, if we've got y equals root x, then that means we know that x equals y squared, and that means we don't actually have to find any more information here. We don't need to find the x value here, we don't need to find the x value there, we don't need to find the area of two rectangles, and it's just more to carry around in your head. So here we can find the area by integrating y squared with respect to y, this time from 1 to 3. Right, so in this case this approach might be a bit more simple than having to do all the rectangles, subtracting areas, or rotating, right? It's just a quite straightforward definite integral at this point. Once you've figured out the x equals y squared bit, x is a function of y, then it turns into a nice plain definite integral. So y squared integrates to y cubed on 3, from 3 to 1, sub in 3, sub in 1. So we already did this before. Well, this was 3 cubed was 27 on 3 is 9, minus 1 cubed is 1 on 3 is a third, so that will be 8 1/3 square units. So if you prefer some of the other methods, go ahead and have a go at doing this problem with either rotating or doing rectangles and subtracting an area bounded by the x-axis. And if you do it, oh sorry, minus a third should be, and 8 2/3 it should be. Whichever method you take, if you do it correctly, you should get 8 2/3. Alright, let's have a look at the next one. We've got y equals x squared, y equals 4, and we're bound by the y-axis for all these problems. So let's draw up a diagram of this. Whoops. So we've got y equals x squared, y equals 4, that's y equals 4, that's going to pass through 4, and we're bound by the y-axis along here, so that means we're looking for this area here. So to be honest, personally, I think if this is 0 here, that should be connected. When it's 0, I personally think it's the easiest approach is to just find this value here and do the rectangle, and then minus the area under the curve. But we'll try, just because this is the way it's framed in your textbook that you'll do, we'll try, and it's good equation skills to practice, we'll try representing x as a function of y. So if we've got y equals x squared, and we want to make x a subject to reverse square, we'll have to do x is plus or minus square root of y. However, because we're bound by the x-axis and we're just looking for this bit here, this is only going to be, this bit here is the positive root y bit, and that bit there's the negative root y bit. So we're actually only looking at the positive half of root y, right? It's just there's a positive and a negative part of the root, just like this graph here is y equals positive root x, and negative root x would be the other half underneath there. Okay, so since we've represented x as a function of y, we can integrate it with respect to y just across the range of values here from 0 up to 4. So we'll have the area is from 0 to 4 of positive root y dy. So half, add 1 to the power, is 3 on 2. Divide by the new power, 3 on 2. And now here again we can write this as y cubed. The 2 in the denominator means square root, and divide by 3 on 2 is the same as times by the reciprocal 2 on 3. And now we can substitute in 4 and minus substituting in 0. So now here we get again, put this in your calculator, but 4 cubed is 64, square root of 64 is 8, 8 times 2 is 16, 16 over 3 minus this bit will all be 0. So this will be 16 on 3 square units. Right, so if you want to again try using a different method, that's perfectly fine. Like I said, me personally, I would, because I'm anticipating that if I do this as a function of y, I'm going to have to integrate root y, and integrating root y is 2 root y cubed on 3 is a bit more ugly than if I just integrated x squared as x cubed on 3 and then subtracted away the bit below from the rectangle, which will be a 4 by I think 2 rectangle. So you can do the same thing in different ways and get the same results. Have a go if you prefer that. Alright, question 4. What have we got? Y equals x squared. And we're going from x equals negative 2, so x equals negative 2, to 0. Something seems off about that. Bound by the y. Did I write this one down wrong? This seems odd, because if it's bound by the y-axis, it can't be y should equal negative 2 either. That won't make any sense. Don't worry about question 4. Mr. Godfrey made a mistake. Alright, so there's only 3 examples there, but hopefully it was helpful seeing the different methods there. So be flexible and be able to use them all. Again, I personally prefer subtracting some rectangles, but yeah, there is different ways you can manipulate the shape geometrically to have either by rectangles or rotating to be able to just turn it into an x-axis bound problem. But you can still do it like this with a slid across. You can actually still do it like a basically doing the same process you do, but just once you've identified x as a function of y instead, and then it's just a definite integral. And of course, if you ended up with a negative number, just like with areas bound by the x-axis, you'd need to take the absolute value. So of course, it's a positive value. Alright, well, that's it for this one. Bye.